Hey, welcome to Dynamics Lesson 3 on inclined planes. So we're going to be looking at breaking up forces into two dimensions, which is the bigger picture idea in this unit. And Physics 12 differentiates from Physics 11 in the sense that we look at forces in two dimensions. So this is just continuing along those lines. And we're going to look at forces along inclined planes. So that's the focus of today's lesson. So let's begin. Recall from previous lessons, objects do not change velocity unless a force acts upon them. Any problems that involve force of friction, the direction is always opposite of the direction of motion or potential motion. So friction always acts opposite the direction of motion or potential motion. That means if an object is not moving but about to move or could move, it's going to act opposite the direction that it could move. When an object starts to slip, FFS, which is your static frictional force, max, is reached. To find the acceleration of an object, first calculate the net force on the object from the vector diagram, then use Newton's second law to calculate the acceleration of the object. Note, when solving, the acceleration of the object is in the same direction as the net force. Only two forces are acting in the direction of motion, FGX and FF. So I'm going to explain what this notation means, FGX and FF is force of friction. But we're essentially going to break up forces along an inclined plane in two dimensions. So the direction down the plane is going to be the x direction, and the direction perpendicular to the plane is going to be the y direction. And we can essentially make anything the x or y direction in physics. It's up to the scientist doing the calculations to determine what he or she sees fit as being most convenient. A free body diagram shows all the forces acting on an object. When working in two dimensions, we use free body diagrams to identify all the forces acting on an object and then construct force vector diagrams to add the force vectors together. The resultant force can be drawn in order to close the diagram and identify the force causing acceleration. So here's an example of a free body diagram of a skier traveling down a mountain slope. So this concept is going to be a little bit challenging today, so you really have to focus on the examples that I provide today. But if we look at the skier traveling down the slope, we can ignore friction. We can assume that it's negligible or close to zero. So there's no frictional force. So there's two forces acting on the skier. There's a force of gravity that acts straight down towards the earth, Fg, and there's a normal force that acts perpendicular to the surface. Normal forces always act perpendicular to a surface, and so there's a normal force acting on the skier, Fn. And that is shown in this diagram here. So you have the normal force and you have the force of gravity. Okay? And if we resolve the two forces and add them head to tail, as you learned to do that in the past, the resultant force, the net force, is acting parallel down the slope, and that resultant force is the net force, which is the sum of Fg and F normal together, and that resultant force is what causes the skier to travel down the slope. And that resultant force, we will learn shortly, is the component of the gravitational force acting parallel to the surface, which causes the skier to travel down the slope. It'll make more sense as I explain. So an object on a frictionless inclined plane experiences two forces, the force of gravity and the normal force. As in the free body diagram for the skier, the net force is directed down the slope. Using the principles of geometry, calculate the angle shown in the diagram. Show all of your work. So essentially what we can do here is, and what we will do in these examples, is we will break down the force of gravity into two components. One component is Fgx, which is the force of gravity acting parallel to the surface of the inclined plane. So the x direction is this direction traveling down the inclined plane, and the y direction is perpendicular to the inclined plane. And we do that for convenience because the x direction is the direction that the object is traveling. It's traveling down the inclined plane, so it makes it easier to solve these problems if we use the direction parallel to the inclined plane as being the x direction and perpendicular to the plane as being the y direction. So Fg, the force of gravity, can be broken down into two components. We can break it down into one component where it's acting perpendicular to the inclined plane, and another component where it's acting parallel to the inclined plane. So this force of gravity is acting straight down towards the Earth, but relative to the inclined plane, it's at an angle to the inclined plane, so we can break this angle down, alpha, and we can find the parallel component and, or sorry, the perpendicular component and the parallel component of the force of gravity. So the force of gravity essentially it breaks down into two parts. One part of that force acts to pull the block down the ramp, and the other force acts to push the block against the surface of the inclined plane. Okay? So what I want you to do is I want you to pause the video and try to determine what this angle is and try to figure out what that angle exactly is equal to. So pause the video here and then I will explain shortly. Okay, if you did that correctly, you should find that in this case theta equals 30 degrees, which is the angle of the incline above the horizontal. And if you did your geometry correctly, alpha is equal to that same angle, 30 degrees. And the way that you can figure that out is if you think about this FG makes an angle of 90 degrees with the horizontal. So if this angle is 90, then this angle here, and we can just call that beta, is equal to 180. So beta equals 180 minus 90 minus 30, which equals 60 degrees. Okay, so beta equals 60 degrees. And if you look at this angle here, this angle between FGY and the surface of the incline is 90 degrees. So this angle is 90 degrees. And so if we calculate alpha, alpha is just equal to 90 degrees minus beta, which equals 90 degrees minus 60 degrees, which equals 30 degrees. There may be an easier way to solve that. It's not coming to mind right now. This might be a little bit more complicated than it needs to be, but that's one way to solve it. There's a couple of ways to look at it. And so if you found a different way and it works, that's great. So theta equals 30 degrees. Or alpha rather, alpha equals 30 degrees. On the inclined plane, the normal force is the reaction force to the component of the force of gravity that is perpendicular to the surface of the incline, Fgy. As you should have found, the angle between the force of gravity and the component of gravity perpendicular to the plane is equal to the inclination of the angle of the plane. Okay, determine the acceleration of a 12 kilogram block sliding down a plane surface angled at 47 degrees to the horizontal. Assume that friction is negligible. Okay, so we have a block that is sliding down an inclined plane. There's two forces on the block. And we break up Fg into Fgy and Fgx, okay? And from the free body diagram, the only force in the direction of motion is Fg, okay? So Fg is the only force acting in the direction of motion. The Fgy is perpendicular to the motion, Fn is perpendicular to the motion, so these two forces do not affect the motion of the object. It's only Fgx that affects the motion of the object down the ramp because there's no friction. So F net equals Fgx, and we can calculate F net, which is equal to Fgx, which equals Fg times sine 47 degrees. And again, the way that we do that is we look at our diagram, and this angle alpha is equal to 47 degrees. So Fgx is the opposite side. This is a 90-degree triangle. And so Fgx is equal to Fg, the force, which is our hypotenuse here, times sine 47. Okay, and so we can plug in our values and solve for F net, which is equal to 86 newtons. Using Newton's second law, we can solve for acceleration. By substitution, we get acceleration equals 7.2 meters per second squared. Okay, next we're going to look at the dynamics of sliding down an inclined plane with friction. When solving these dynamics problems, you must include the effects of the normal force, as the force of friction depends on the normal force. Recall that friction is equal to mu Fn. When solving more complex dynamic problems, it is useful to follow a problem-solving routine. Using the steps below as a guide, calculate the acceleration of a 12 kilogram block placed on an incline of 47 degrees if the coefficient of friction between the block and the plane is 0.3. So we can first draw the free body diagram. The only difference between this free body diagram and the one we saw earlier is that now there's a force of friction, and friction always acts opposite the direction of motion. Okay, and so in this case, friction will depend on Fn. Okay, that's what it will essentially depend on. We can draw a free body diagram labeling only the forces acting on the object. Determine the direction of motion, then calculate the components of each force in the direction of motion. calculate the components of the force of gravity down the incline. So Fgx equals Fg sine 47, just like we did in the last example. And we can solve, and that's equal to 86 newtons. We can calculate friction up the incline. F friction equals mu k times Fn. Fn is simply equal to Fgy, which equals mg times cos 47 degrees. It's an action-reaction force, so gravity is pushing against the surface. Fn is just an equal and opposite force to the force of gravity, perpendicular to the surface, which is equal to mg cos 47. And then we can plug in Fn into our equation for F friction and then solve. So we get 24.1 newtons. Next, calculate the net force by adding or subtracting the components of the force in the direction of motion. In other words, the x direction down the inclined plane. F net equals Fg minus F friction, which equals 86 newtons minus 24.1 newtons, which equals 61.9 newtons. So just to clarify what's happening here is you have two forces acting down the incline. You have F friction pushing up the incline, F friction, which in this case is equal to 24.1 newtons. And the direction of motion is being caused by the force of gravity, Fgx, which is 86 newtons. By subtracting them, we get the net force on the object. And the direction of motion in general is taken to be the positive direction. So this might be a bit different from what you're used to because the downward direction is usually negative, but in this case, down the ramp is the positive direction. And then we can calculate the acceleration, which equals F net divided by mass. And we get 5.2 meters per second squared. And that concludes the presentation.